What if everything you think you know about space is just the tip of an unimaginable cosmic iceberg? Picture the universe as a vast, ever-growing bubble. But here's the twist. Bubbles expand into something, right? So what lies beyond the edges of our reality? This isn't just science fiction. It's one of the most profound mysteries in modern cosmology. The universe is expanding, and not just slowly, it's accelerating, stretching the fabric of space itself faster than we can comprehend. But if space is all there is, how can it grow into nothingness? Or is it nothingness at all? Think about the last time you blew up a balloon. As it inflates, the surface stretches, and every dot on that balloon moves away from every other dot. Now imagine you're one of those dots, living on that expanding surface. You'd see everything around you drifting apart, but here's the catch. You'd never see the outside of the balloon. That's the bizarre reality we're stuck with when we ask what the universe is expanding into. Our entire existence might be like that balloon's surface, a dimension we can't escape or perceive beyond. And yet, scientists refuse to accept that the answer ends there. From the echoes of the Big Bang to the invisible force of dark energy pushing galaxies apart, every clue we uncover only deepens the mystery. So let's take a step into the unknown together. Over the next few minutes, we'll venture beyond the limits of human intuition, where time bends, dimensions multiply, and the very idea of outside might not even make sense. We'll unravel the leading theories, some brilliant, some baffling, about what could lie beyond the cosmic horizon. Could there be other universes jostling against ours in some unimaginable multiverse? Or is space itself creating new room as it expands, like a magic trick with no magician? One thing's for certain, by the end of this journey, you'll never look at the night sky the same way again. The universe isn't just expanding, it's inviting us to question everything we thought we knew. To understand what the universe is expanding into, we first have to rewind time way back to the very beginning. 13.8 billion years ago, in a fraction of a second too small to fathom, the entire cosmos erupted into existence from a point smaller than an atom. This wasn't an explosion in empty space. Space itself was born in that instant, unfurling like an infinite sheet being stretched in all directions at once. We call this the Big Bang, but the name can be misleading. It wasn't a bang in the traditional sense, with sound and debris flying outward. Instead, it was the sudden appearance of space, time, and energy, all expanding together in a fireball of unimaginable density. One of the most crucial pieces of evidence for this cosmic birth is the cosmic microwave background, a faint glow of radiation that fills the entire sky. This is essentially the afterglow of the Big Bang, cooled down over billions of years but still detectable as a whisper of heat left over from the universe's infancy. Then there's redshift, the stretching of light from distant galaxies as they move away from us. The farther a galaxy is, the faster it appears to be receding, like dots on that inflating balloon drifting apart. These observations tell us that space itself is stretching, carrying galaxies along with it, not because they're moving through space, but because the space between them is growing. But here's where things get even stranger. The Big Bang didn't happen at a single point in space, it happened everywhere at once. Imagine the entire universe compressed into an ultra-dense speck, and then suddenly, all of space expanded simultaneously. There was no center, no edge, just an eruption of reality unfolding in every direction. This means that when we look deep into space, we're also looking back in time, catching glimpses of the universe when it was younger, hotter, and more crowded. So if space is stretching, what's it stretching into? That's the puzzle. The Big Bang didn't just create matter and energy, it created space itself. And if space is all there is, then the idea of an outside might not even apply. It's like asking what's north of the North Pole. The question itself might be flawed because our intuition, shaped by the world we see every day, isn't equipped to grasp the true nature of the cosmos. Yet scientists keep pushing, probing the edges of our understanding, searching for answers in the echoes of the Big Bang and the invisible forces shaping our universe's fate. Edwin Hubble's telescope revealed something astonishing in the 1920s. Galaxies weren't just floating in space, they were racing away from us, and the farther out he looked, the faster they seemed to be moving. This wasn't just a random drift of cosmic objects. Hubble had stumbled upon a fundamental truth about the universe. Space itself was stretching, carrying galaxies along like raisins in a rising loaf of bread. But here's the crucial distinction. This isn't about galaxies moving through space like cars on a highway. It's space itself expanding, creating more room between distant points over time. To wrap your head around this, imagine a rubber sheet covered with tiny dots. If you stretch the sheet evenly, every dot moves away from every other dot, but the dots themselves aren't crawling across the material. They're being dragged apart by the stretching underneath them. That's metric expansion, the real engine behind the universe's growth. Nearby galaxies, like our neighbor Andromeda, aren't swept away because gravity binds us tightly enough to resist the cosmic stretch. But venture far enough out, and the expansion dominates, sending galaxies fleeing at speeds that eventually outpace even light itself. Hubble's law captures this phenomenon with a simple equation. The farther a galaxy is, the faster it recedes. But the real shock came in the late 1990s when astronomers studying distant supernova discovered something even wilder. The expansion isn't just continuing, it's speeding up. Something invisible, dubbed dark energy, is pushing the universe apart with relentless force, like an anti-gravity effect woven into the fabric of space. So why does this matter? Because the fate of the cosmos hinges on this acceleration. If dark energy keeps strengthening, it could one day tear apart galaxies, stars, even atoms in a theoretical big rip. Or perhaps expansion will slow, leading to a cold, silent fade out. Right now, we're left with more questions than answers, but one thing's clear: the universe isn't just growing. It's evolving in ways that defy our deepest intuitions, rewriting the rules of reality with every passing second. The universe we can see, the one filled with swirling galaxies and twinkling stars, is just a tiny fraction of what might actually be out there. This bubble of visibility, stretching roughly 93 billion light-years across, is what we call the observable universe. But here's the catch: it's not the whole story. Beyond the farthest light that's had time to reach us since the Big Bang, there could be vastly more space, more galaxies, even more versions of reality we'll never glimpse. The observable universe is like standing in a foggy forest. You can only see so far before the mist swallows everything, but the forest itself might stretch on forever. This raises a mind-bending question. Is the entire universe infinite, or just incredibly large but still finite? If it's infinite, then no matter how far you traveled, you'd never hit an edge. Just more galaxies, more emptiness, more of the same cosmic sprawl. An infinite universe doesn't expand into anything because by definition, it's already everywhere. Space just stretches, growing roomier without needing an outside to grow into. But if the universe is finite, things get even stranger. Imagine space as the surface of a balloon, again finite, but without a boundary. No matter which direction you go, you'd never reach a wall or a drop-off. Instead, you might eventually loop back to where you started, like an astronaut circumnavigating a cosmic globe. both possibilities defy our everyday experience. An infinite universe feels overwhelming, like trying to count numbers that never end. A finite one feels claustrophobic, as if reality is secretly folded in on itself. But here's where it gets truly fascinating. Even if the universe is finite, it could still be so vast that the curvature of space is undetectable to us, making it seem flat and infinite within our observable bubble. That's why scientists study the cosmic microwave background for subtle warps, hints that space might curve back on itself like a giant, invisible maze. So what does this mean for the expansion? If the universe is infinite, it's not expanding into anything. It's just getting less dense, like thinning out an endless ocean. If it's finite, the expansion still doesn't require an outside. Space itself is the stage, and the stage is growing, no extra room needed. This reshapes the very question we started with. Instead of asking what the universe is expanding into, we might need to ask, is into even the right word? The answer could rewrite not just our maps of the cosmos, but our understanding of existence itself. Is the universe expanding into something, or is that the wrong way to frame the question entirely? At first glance, it seems logical to picture the cosmos like a balloon inflating inside a room. But here's the problem. If the universe truly contains all of space and time, then there is no room for it to expand into. This is where our everyday intuition collides head-on with the bizarre reality of cosmology. The key lies in understanding that space isn't just a backdrop for the universe, it is the universe. When we say space is expanding, we're not talking about something spreading into a void beyond. Instead, the fabric of reality itself is stretching, creating more space between points that were already there. Think of it like a loaf of raisin bread rising in the oven. The dough represents space and the raisins are galaxies. As the bread expands, every raisin moves away from every other raisin, not because they're traveling through the dough, but because the dough itself is swelling. Now imagine the entire loaf is all that exists. There's no oven, no countertop, just the bread. That's the universe. There's no outside for it to expand into because the loaf defines reality. This is why cosmologists often say the question might be misleading. The universe isn't expanding into anything. It's simply becoming less dense as space stretches. But what if there's more to the story? Some theories in physics suggest our universe might be embedded in something larger, a higher dimensional space, or even a multiverse. Imagine our three-dimensional universe as a sheet of paper floating in a vast, unseen fourth dimension. In this scenario, space could stretch into that higher dimension, like a crumpling piece of paper expanding in a room we can't perceive. String theory and brain-world cosmology explore these ideas, proposing that our universe is just one membrane, or brain, drifting in a higher dimensional bulk. If true, the expansion we observe might be the motion of our brain through this hidden realm. Then there's the Multiverse Hypothesis, which suggests our universe is just one bubble in a frothing sea of other universes, each with its own laws of physics. In this view, cosmic expansion could be the result of our bubble universe nudging against others in an unimaginably vast landscape. But here's the catch. Even if these theories are correct, the something our universe is expanding into wouldn't be space or time as we know it. It would be a realm so foreign that words like outside or into might not even apply. Other physicists argue that the question itself stems from a flawed analogy. We're used to objects moving through space, so we assume the universe must be doing the same. But space-time isn't an object, it's the stage on which everything plays out. Asking what's beyond the universe might be like a character in a video game asking what's outside the screen. The game world doesn't expand into the player's living room, it just renders more pixels as needed. Similarly, the universe might not need an outside to grow. It could simply generate new space as it goes, like a never-ending roll of cosmic fabric unfurling from within. So where does this leave us? The truth is, we don't yet know if the question has an answer or if it's even the right question to ask. What's clear is that our language and intuition, shaped by life on Earth, might be hopelessly inadequate for describing the true nature of reality. The universe doesn't owe us an answer that fits neatly into human concepts, but that's what makes this mystery so thrilling. Every time we peel back one layer, we find another, deeper puzzle waiting, one that challenges not just what we know, but how we think. What if our universe isn't alone, but just one page in an endless cosmic library? The Multiverse Hypothesis turns the mystery of cosmic expansion into something even grander, suggesting that what we call the universe might be a single bubble in a frothing sea of others, each with its own laws of physics, its own history, even its own version of reality. This isn't just wild speculation. It's a serious, though still unproven, framework that emerges from some of physics' most ambitious theories. Take eternal inflation, for example. Picture the Big Bang not as a one-time event, but as a never-ending process, like a pot of water boiling eternally, with new universes bubbling up continuously. In this view, our universe is just one bubble among countless others, each inflating like a balloon within an unfathomably vast metaspace. String theory adds another layer to this cosmic tapestry. It suggests that our universe might be a three-dimensional brain floating in a higher dimensional realm called the bulk. Other brains could exist mere millimeters away from us in these unseen dimensions, each hosting its own universe, utterly invisible yet tantalizingly close. Collisions between these brains might even explain cosmic anomalies like the Big Bang itself. Imagine two sheets of paper, our universe and another, floating in a fourth dimension, brushing against each other with enough force to ignite an entire reality. But how could we ever test such ideas? The challenge is that these other universes, if they exist, might be forever beyond our reach. Light from them can't cross the void between bubbles, and the laws of physics there could be so alien that matter as we know it couldn't survive. Yet some scientists hunt for subtle clues, anomalies in the cosmic microwave background that might bear the scars of a long-ago collision with another universe, or strange gravitational echoes leaking through the higher dimensional bulk. The multiverse isn't just a scientific idea, it's a philosophical lightning rod. For some, it's a thrilling reminder of how much we don't know. For others, it's a frustrating dead end, a theory so flexible it can't be disproven, making it more metaphysics than physics. But whether it's ultimately true or not, the multiverse reshapes the question of what our universe is expanding into. If other realities exist out there, then cosmic expansion might be less like a balloon growing in empty space and more like a soap bubble jostling in a sink full of them, each expanding into a shared, invisible medium we can't yet perceive. And that's the real twist. If the multiverse is real, then nothingness might not exist at all. What we've been calling the outside could be a bustling arena of other universes, each with its own story, its own mysteries. Our cosmic horizon wouldn't be a wall, just the limit of what we can see, with untold wonders lying just beyond. It's a humbling thought. After all, if we're still struggling to understand our own universe, how could we possibly grasp what lies past it? Yet that's the beauty of the multiverse hypothesis. It doesn't just offer answers, it invites us to dream bigger, to question deeper, and to wonder if the ultimate truth about reality is stranger than we've ever dared to imagine. Imagine living your entire life confined to the surface of a piece of paper, unable to look up, down, or beyond its edges. To you, reality would seem flat, two-dimensional, with no concept of the vast three-dimensional world surrounding it. Now take that same leap of imagination and apply it to our universe. What if the three dimensions we know, length, width, and height, are just the visible layers of something far more complex? This is the tantalizing possibility raised by string theory, which proposes that our universe might be embedded in a higher dimensional realm called the bulk, with extra dimensions curled up so tightly we've never noticed them. Think of it like this: an ant crawling on a telephone wire sees only a one-dimensional line, but from our perspective, the wire exists in 3 dimensions. Similarly, our universe might be like a 3-dimensional brain, short for membrane, drifting in a space with 4, 5, or even 10 dimensions. If that's true, then the expansion of our universe could be more than just stretching. It might be movement through these hidden dimensions, like a sheet of paper fluttering in an unseen breeze. But how would higher dimensions explain what the universe is expanding into? Picture a soap bubble floating in a room. The bubble's surface represents our 3-dimensional universe, while the air around it is the bulk. As the bubble expands, its surface grows into the room's space, except in this analogy, the room is a dimension we can't perceive. In string theory, gravity might even leak into the bulk, which could explain why it's so weak compared to other forces. It's spreading out into dimensions we can't see. The math behind these ideas is elegant, but the challenge is proving they're more than just equations on a page. Extra dimensions, if they exist, would be unimaginably small, perhaps a billionth of a billionth the size of an atom, or else we'd have noticed them by now. Some experiments, like particle colliders, hunt for evidence of these dimensions by searching for missing energy that might vanish into them. Others look for subtle deviations in gravity's behavior at microscopic scales. So far, no smoking gun has been found, but the search reshapes how we think about reality. Even if higher dimensions exist, do they truly answer the question of what's outside our universe? It's a paradox. If the bulk is a higher dimensional space, then it's still part of a larger reality. So what contains that? The rabbit hole goes deeper, revealing that every answer might just lead to another layer of mystery. Yet that's the thrill of cosmology. Whether these dimensions are real or not, they push us to rethink the very fabric of existence, reminding us that the universe is far stranger and more wonderful than it seems. The idea of nothingness might sound simple: just empty space, a void where nothing exists. But in physics, nothing is anything but empty. Take the quantum vacuum, for instance. At the tiniest scales, even the emptiest regions of space are seething with activity. Particles pop in and out of existence in a frenzy of quantum fluctuations, borrowing energy from the universe for fleeting moments before vanishing again. This isn't poetic metaphor, it's a measurable phenomenon, with real effects like the Casimir force, where 2 metal plates placed close together in a vacuum are subtly pushed together by the particles winking into existence around them. So if nothing is this lively, what does that say about the space our universe is supposedly expanding into? Some philosophers argue that nothingness is a concept our brains struggle to grasp. We're wired to think in terms of containers and contents, a box holding objects, a room filled with air, but the universe might not play by those rules. If space and time began with the Big Bang, then asking what's outside is like asking what's north of the North Pole. The question assumes a framework that doesn't apply. Even the word expand can mislead us. It implies movement into pre-existing space. But cosmic expansion might be more like numbers multiplying on a ruler, creating new increments without needing extra paper. This leads to a radical possibility. Maybe the universe isn't expanding into anything at all. Instead, it's generating space as it goes, like a treadmill that builds its own track while running. In this view, the nothingness beyond isn't a void waiting to be filled, it's a placeholder for a question that doesn't need an answer. The physicist Max Tegmark puts it bluntly: asking what's outside the universe is like asking what's outside a circle. The concept just doesn't map onto reality, yet the human mind rebels against this. We crave edges, boundaries, a sense of beyond. That's why theories like the multiverse or higher dimensions feel so compelling. They offer a kind of cosmic furniture, a place for our universe to sit. But the truth might be stranger. If the quantum vacuum teaches us anything, it's that nothing is fertile ground for reality. The universe could be its own container, its own context, with no need for an outside. After all, if space and time are properties of the universe itself, then the idea of an outside might not just be unknown, it could be fundamentally meaningless. So where does this leave our original question? Perhaps the paradox isn't in the answer, but in the question itself. The universe doesn't expand into nothingness because expansion doesn't require a destination. It's not filling a void, it's rewriting the rules of what existence means, and that's the real mystery. Not what lies beyond the cosmic horizon, but why we're so certain there has to be a beyond it all. Einstein's theory of general relativity revolutionized our understanding of gravity, not as a force, but as the curvature of spacetime itself. Picture a trampoline with a bowling ball at its center. The ball creates a dip in the fabric, and if you roll a marble nearby, it spirals inward. That's how massive objects like stars and planets warp the cosmos, bending the paths of everything around them. But here's where it gets mind-bending. Einstein's equations didn't just describe gravity, they implied something astonishing about the universe as a whole. When he solved them, they pointed to a cosmos that couldn't stay still. It had to be either expanding or contracting, like a breath held too long before the inevitable exhale. This was a problem for Einstein. In 1917, the prevailing belief was that the universe was static, eternal, and unchanging. The idea of an expanding cosmos seemed absurd, so he tweaked his own equations, adding a fudge factor he called the cosmological constant. This mathematical term acted like an anti-gravity force, balancing the universe against collapse or runaway expansion. It was a clever fix, but one he'd later call his greatest blunder. Because just over a decade later, Edwin Hubble's observations proved the universe wasn't static at all. Galaxies were racing apart, and Einstein's original equations without the constant had been right all along. Yet the story doesn't end there. In the late 1990s, astronomers made a discovery that turned cosmology on its head. The universe's expansion wasn't just continuing, it was accelerating. Suddenly, the cosmological constant wasn't a mistake, it was a prophecy. Scientists realized that empty space itself might contain a repulsive energy, a modern incarnation of Einstein's discarded term, now called dark energy. This invisible force now makes up 68% of the universe's energy budget, pushing galaxies apart faster and faster. What's fascinating is how this mirrors the scientific process itself. Even Einstein, a titan of physics, clung to assumptions that later proved wrong. His reluctance to accept an expanding universe shows how deeply intuition can mislead us, especially when confronting realities beyond everyday experience. But science, unlike genius, is self-correcting. Ideas get tested, evidence accumulates, and sometimes the very concepts we dismiss return in ways we never anticipated. The cosmological constant's resurrection as dark energy is a humbling reminder. The universe doesn't care about our preconceptions. It reveals itself on its own terms, often in ways that defy even the boldest imaginations. So did general relativity predict cosmic expansion? Absolutely, but with a twist. The math was always there, hidden in the equations like a buried treasure. It took decades of observation, debate, and a few brilliant mistakes to uncover it. And that's the beauty of Einstein's theory. It's not just a description of gravity or the universe's structure. It's a living framework, one that keeps surprising us with new insights, proving that even the most profound truths can remain invisible until we're ready to see them. The late 1990s brought a revelation that shattered cosmology's status quo. The universe isn't just expanding, it's doing so faster and faster, as if some unseen hand were pressing hard on the cosmic accelerator. This discovery, which earned its researchers the Nobel Prize, pointed to something even more baffling than dark matter: dark energy, an invisible force saturating empty space itself, pushing galaxies apart with relentless strength. Today, dark energy accounts for roughly 68% of the universe's total energy content, dwarfing everything else: stars, planets, even the enigmatic dark matter that binds galaxies together. But what exactly is this mysterious energy, and how does it warp the fabric of reality? One leading explanation ties back to Einstein's old cosmological constant, a repulsive energy woven into the vacuum of space. Picture empty space not as true nothingness, but as a bubbling quantum foam where particles fleetingly appear and vanish. According to quantum theory, this activity imbues every cubic centimeter of the universe with a tiny amount of energy. Stack up enough cubic centimeters across cosmic distances, and you get a repulsive force powerful enough to stretch spacetime itself. If this interpretation holds, dark energy isn't a thing so much as a property of space, a steady pressure that grows as the universe expands, ensuring acceleration never stops. But not all scientists are convinced. Some propose dark energy might be quintessence, a dynamic field that changes over time, unlike the static cosmological constant. Imagine a cosmic weather system where the strength of dark energy ebbs and flows, sometimes pushing galaxies apart fiercely, other times subtly. This could explain why the universe's expansion rate seems to have shifted across cosmic epochs. If quintessence is real, dark energy might one day weaken or even reverse, potentially leading to a big crunch where the universe collapses back on itself, a dramatic twist in the cosmic story. Then there's the possibility we've misunderstood gravity itself. Einstein's theory of general relativity has passed every test so far, but what if it breaks down on the largest scales? Modified gravity theories suggest that what we call dark energy might actually be a sign that gravity behaves differently over vast distances, weakening just enough to mimic an anti-gravity effect. It's like realizing the rules of chess change slightly when the board expands a subtle shift with universe-altering consequences. The stakes couldn't be higher. If dark energy remains constant, the universe faces a big freeze: galaxies vanishing over the horizon, stars burning out, and space stretching so thin that even atoms tear apart. If it strengthens, a big rip could shred reality itself. Yet for all its power, dark energy leaves almost no trace we can detect directly. Its presence is inferred solely through its cosmic fingerprints, the way distant supernovae appear dimmer than they should, or how galaxy clusters seem to be flung apart. This invisibility makes dark energy one of science's greatest puzzles. We're like detectives trying to solve a case where the culprit leaves no fingerprints, no footprints, just the aftermath of their actions. Future telescopes, like the European Space Agency's Euclid mission, aim to map dark energy's influence with unprecedented precision, hunting for distortions in the light of billions of galaxies. Meanwhile, particle accelerators probe the quantum vacuum for clues, hoping to catch dark energy in the act of shaping the universe. What's clear is that dark energy isn't just another mystery. It's the defining force of our cosmic era, sculpting the fate of everything we see. Whether it's Einstein's resurrected constant, a shifting quantum field, or a flaw in our grasp of gravity, one thing's certain: the answer won't just tell us what the universe is expanding into. It'll reveal what it's ultimately made of. The universe isn't just expanding, it's racing toward an uncertain destiny, and the driving force behind that fate is dark energy. If its relentless push continues unchecked, the cosmos could face one of three dramatic endings: the Big Freeze, the Big Rip, or the Big Crunch. Each scenario paints a vastly different portrait of reality's far future, stretching across timescales so immense they dwarf the entire history of life on Earth. Let's start with the Big Freeze, also known as heat death. In this slow-motion fade-out, dark energy keeps accelerating expansion until galaxies vanish over the cosmic horizon, leaving our Milky Way an isolated island in an ever-darkening void. Stars burn through their fuel one by one until even the longest-lived red dwarfs flicker out. Black holes evaporate over eons, leaking radiation into an ever-colder expanse. Eventually, space becomes a near-perfect vacuum, with particles so sparse that an atom might travel billions of light years before encountering another. Time itself could lose meaning in this frozen, silent wasteland, a universe where entropy maxes out and nothing happens ever again. But what if dark energy doesn't just persist? What if it grows stronger? That's the nightmare scenario of the Big Rip. Here, dark energy's repulsive force becomes so overpowering that it doesn't just separate galaxies, it shreds reality itself. First, galaxy clusters are torn apart, then individual galaxies. As the acceleration intensifies, stars are ripped from their orbits, planets from their stars. In the final moments, even atoms and subatomic particles are torn asunder, their bonds overcome by the stretching of space itself. The universe wouldn't just end with a whimper or a bang, it would dissolve into a sea of disconnected particles, each hurled into an inescapable void. Yet there's a third possibility, the Big Crunch. If dark energy weakens over time, or if gravity somehow regains the upper hand, the universe's expansion could slow, halt, and reverse. Galaxies would begin rushing toward one another, colliding in a cosmic traffic jam of epic proportions. Space would heat up as matter packs tighter, until the entire universe is compressed back into a seething, ultra-dense state, a mirror of the Big Bang, but in reverse. Some theories even suggest this could trigger a new Big Bang, birthing another universe in an endless cycle of collapse and rebirth. Which outcome is most likely? Right now, the evidence leans toward the Big Freeze. Observations suggest dark energy's strength has held steady for billions of years, making a sudden shift toward a Big Rip or Big Crunch seem improbable. But cosmology humbles certainty. Dark energy could be more dynamic than we realize, or gravity might hide secrets we've yet to uncover. The only way to know is to keep probing the cosmos, measuring the expansion rate with ever greater precision, searching for clues in the light of ancient supernova and the large-scale structure of the universe. These aren't just abstract thought experiments, they're windows into the deepest nature of reality. If the Big Freeze is our fate, then the universe is a one-way trip toward stillness. If the Big Rip looms, then space itself is more fragile than we imagined. And if the Big Crunch awaits, then time might be circular, with endings birthing new beginnings. Whatever the answer, it reminds us that the universe isn't static. It's a story still being written, with chapters that stretch far beyond the span of human existence. And in that story, dark energy isn't just a footnote, it's the force holding the pen. The Hubble Tension might sound like a minor scientific disagreement, but it's actually a cosmic puzzle that's keeping astronomers up at night. Here's the problem. When we measure how fast the universe is expanding today using nearby supernova, we get one number. But when we calculate it using the ancient light of the cosmic microwave background, we get a different, slightly smaller value. These aren't just tiny margins of error. The gap between them is significant enough to suggest something fundamental might be missing from our understanding of the cosmos. It's like using two different rulers to measure the same object and getting conflicting results, except in this case, the object is the entire universe. So why does this discrepancy matter? Because both methods are incredibly precise, and they're built on pillars of well-tested physics. The supernova approach relies on watching how the light from these stellar explosions dims over vast distances, giving us a direct read on how fast space is stretching around us. Meanwhile, the cosmic microwave background, the afterglow of the Big Bang, lets us extrapolate the expansion rate by studying the universe's baby pictures, frozen in time from when it was just 380,000 years old. These two methods should agree, but they stubbornly refuse, leaving scientists scrambling for answers. One tantalizing possibility is that this tension hints at new physics lurking just beyond our current theories. Maybe dark energy isn't constant after all, but has evolved over time in ways we didn't anticipate. Or perhaps there's an unknown particle, a relic from the early universe, that subtly tweaks the cosmic expansion rate. Some theorists even speculate about a dark radiation that flooded the cosmos in its infancy, leaving fingerprints in the microwave background but fading away before supernova could feel its influence. These aren't wild guesses, they're serious hypotheses born from the need to explain why our two best cosmic yardsticks disagree. Then there's the humbler explanation: maybe we've overlooked something in our measurements. Dust in space could be dimming supernova more than we've accounted for, throwing off distance calculations. Or perhaps the cosmic microwave background holds hidden wrinkles we haven't fully decoded. Even the way we measure distances to nearby galaxies, the foundation of the supernova method, might need reevaluation. After all, astronomy is a game of collecting faint whispers of light across unimaginable distances, and sometimes the smallest errors cascade into big disagreements. The stakes couldn't be higher. If the Hubble tension is real, if it's not just a measurement fluke, it could mean our standard model of cosmology is incomplete. That model, known as lambda CDM, has been spectacularly successful at explaining everything from galaxy formation to the large-scale structure of the universe. But like Newton's laws before Einstein, even our best theories might only be approximations of a deeper truth. Resolving this tension could open doors to discoveries as profound as dark energy itself, rewriting textbooks in the process. Right now, telescopes and satellites are racing to gather more data, from next-generation observatories like the James Webb Space Telescope to ambitious sky surveys mapping millions of galaxies. Each new dataset sharpens the picture, helping us weigh whether the tension is a clue to new physics or just a cosmic mirage. One thing's certain: in the hunt to understand the universe's expansion, disagreement isn't a setback, it's an invitation to dig deeper, question harder, and maybe, just maybe, stumble upon the next great revolution in how we see the cosmos. Imagine the universe in its first moments, not as a steadily growing fireball, but as something far more dramatic. In a fraction of a second so small it defies comprehension, space itself exploded outward, stretching faster than the speed of light, doubling in size again and again in a runaway burst known as cosmic inflation. This wasn't just rapid expansion, it was exponential, like a snowball rolling downhill, growing from a speck to a mountain in the blink of an eye. By the time inflation ended, a region smaller than an atom had been blown up to scales larger than our entire observable universe today. But why do scientists believe such a wild event occurred? And how could it possibly leave traces we can still detect billions of years later? The clues lie in the cosmic microwave background, the faint glow of the Big Bang's aftermath. If you look at this ancient light with precise instruments, two things stand out. First, the temperature is almost perfectly uniform across the sky, varying by less than 1 part in 100,000. That's like a cup of coffee left to sit for billions of years, yet somehow staying the same temperature from edge to edge. Without inflation, there's no way heat could have spread so evenly, unless, as inflation suggests, every part of the universe was once crammed together in a tiny space, then stretched apart before temperatures had time to fluctuate. Second, the universe is remarkably flat on large scales, meaning parallel lines stay parallel no matter how far they travel. This geometry only makes sense if space underwent a colossal smoothing process early on, ironing out any curvature like a cosmic steamroller. Inflation does exactly that, stretching any initial bumps or wrinkles so thin they become invisible. Without it, we'd expect to see a universe far more warped, like a funhouse mirror reflecting the chaos of its birth. Yet inflation isn't just about solving puzzles, it also plants the seeds for everything we see today. Quantum fluctuations, those tiny particles popping in and out of existence, were stretched to astronomical scales during inflation. These microscopic ripples became the gravitational wells where matter pooled, eventually forming galaxies, stars, and planets. In a very real sense, the largest structures in the cosmos trace back to quantum jitters magnified by inflation's incredible stretching. Not everyone is convinced, though. Some physicists argue that inflation is too flexible a theory that can explain almost any observation by tweaking its parameters. Others propose alternatives, like bouncing cosmologies where the Big Bang was preceded by a collapse, or emergent universes where space and time crystallize from a deeper, more fundamental reality. One of inflation's original architects, Paul Steinhardt, even became a critic, warning that without testable predictions, the theory risks becoming unfalsifiable, a storytelling device rather than rigorous science. The debate isn't just academic. If inflation is real, it implies the existence of a multiverse, where our universe is just one bubble in an endless froth of others, each with different physical laws. If it's wrong, we might need to rethink the very origin of time. Right now, experiments are hunting for gravitational waves from the inflationary era, subtle twists in spacetime that could confirm the theory beyond doubt. Until then, inflation remains our best explanation for the universe's startling smoothness, flatness, and structure. A fleeting moment when reality outran even its own rules, setting the stage for everything that followed. The shape of the universe isn't just some abstract curiosity, it's the canvas on which all of reality unfolds, determining everything from how light travels across billions of light years to the ultimate fate of the cosmos itself. Picture space as a vast geometric puzzle. Is it flat like an endless sheet of paper, curved like the surface of a globe, or warped like a saddle? Each possibility would bend the fabric of reality in profoundly different ways, altering how galaxies move, how light travels, and even what lies beyond the cosmic horizon. To grasp how scientists measure the universe's shape, think about drawing a triangle. On a flat plane, the angles always add up to 180 degrees. But on a sphere, they'd sum to more. Picture a triangle stretching from the equator to the North Pole. On a saddle-shaped surface, they'd add up to less. Cosmologists apply this same principle to the cosmos, using the oldest light we can see, the cosmic microwave background, as their ruler. Tiny temperature fluctuations in this afterglow form patterns that act like cosmic triangles, spanning billions of light years. After decades of painstaking measurements, the verdict is clear. Within the margin of error, the universe appears astonishingly flat, but this raises a paradox. If space is truly flat and infinite, then it was always infinite even at the moment of the Big Bang. That means the universe didn't start as a tiny point that grew outward. Instead, an already infinite space became less dense as it expanded. Wrap your head around that, an infinity stretching in all directions, getting roomier with time. This bizarre idea challenges our deepest intuitions about beginnings and boundaries. After all, how can something without edges expand? Here's where the balloon analogy breaks down. A balloon's surface is finite but unbounded. It has no edge yet isn't infinite. But a flat, infinite universe has no edge and no boundary of any kind. Expansion in this context doesn't mean spreading into emptiness. It means the space between every point is simply growing. The real mind bender: even if you could travel infinitely fast, you'd never reach an outside, because in an infinite, flat universe, there's no outside to reach. The question of what's beyond becomes meaningless, like asking what's beyond infinity. Yet the story isn't quite that simple. The universe might be only approximately flat, with curvature too subtle for current instruments to detect. Some theories, like cosmic inflation, suggest the observable universe is just a tiny patch of a much grander cosmos that could be curved on scales beyond our horizon. It's like an ant on a basketball. The surface feels flat if you can't see far enough. Future telescopes could hunt for this subtle curvature by mapping the universe on even larger scales, searching for telltale warps in the paths of ancient light. The shape of space also ties directly to its destiny. A closed, spherical universe might eventually collapse in a big crunch. An open, saddle-shaped one would expand forever at an ever-increasing rate. But a flat universe walks a razor's edge, balanced perfectly between these extremes, its fate dictated by the interplay of dark energy and gravity. Right now, the evidence points to flatness, but with a twist. Dark energy's dominance suggests that even a flat universe won't just expand, it'll accelerate, stretching galaxies apart until they vanish from view. So where does this leave our original question? If the universe is flat and infinite, then what's outside isn't just unknown, it might be a nonsensical concept. Space isn't expanding into anything, it's just becoming less dense, like an infinite grid where the squares keep growing. This doesn't make the mystery any less profound. Instead, it reshapes it, forcing us to confront the limits of human intuition when faced with the true scale of reality. The universe doesn't owe us answers that fit neatly into our earthly logic. It's up to us to stretch our minds as far as space itself, at the smallest scales imaginable, where distances shrink to a millionth of a billionth of a billionth of a meter. The universe stops playing by the rules we know. This is the Planck scale, a realm so tiny that gravity, normally the weakest force, becomes as unpredictable as a quantum particle. Here, Einstein's smooth spacetime shatters into a foaming sea of fluctuations, where black holes blink in and out of existence and the very concepts of here and now lose meaning. This is the frontier where our two greatest theories, quantum mechanics and general relativity, meet in a head-on collision, each refusing to yield. But hidden in this chaos might lie clues to one of cosmology's biggest mysteries: what the universe is truly expanding into. One bold attempt to reconcile these warring theories is loop quantum gravity. Picture spacetime not as a continuous fabric, but as a woven tapestry of tiny, indivisible loops. These loops form a network so fine that not even light can perceive the gaps, creating the illusion of smoothness at larger scales. In this view, the universe's expansion isn't just stretching, it's the rearrangement of these fundamental threads, like a cosmic sweater unraveling and reknitting itself. Some models even suggest that before the Big Bang, the universe could have been a collapsed remnant of a previous cycle, bouncing back into expansion when spacetime reached its smallest possible scale. If true, the question of what's outside might transform into something far stranger, a universe that doesn't expand into space, but regenerates space from within. Then there's string theory, with its vision of reality as a symphony of vibrating strings. These strings don't just dance in 3 dimensions but in 10 or 11, their harmonies generating every particle and force we know. In this framework, space-time could be a hologram, a projection from a distant, higher dimensional surface, like a movie playing on the universe's edge. If so, expansion might not be about space growing into emptiness, but about information rearranging itself on a cosmic screen we can't see. Other approaches, like causal dynamical triangulation, simulate space-time as a mosaic of tiny geometric shapes that constantly reshuffle. Think of it as a cosmic game of Tetris where the blocks are chunks of reality themselves, snapping together to build the universe moment by moment. In this model, expansion isn't movement, it's the creation of new blocks from the inside out, with no need for an external void to fill. Yet for all their brilliance, these theories share a common challenge: testing them. The Planck scale is so far beyond our experimental reach that even the most powerful particle colliders are like blunt tools trying to sculpt a snowflake. Some hope that gravitational waves from the early universe might carry fingerprints of quantum gravity, or that subtle anomalies in high-energy cosmic rays could reveal hidden dimensions. Others look for mathematical consistency, searching for clues in the elegant symmetries of equations. What's remarkable is how each theory reshapes the question itself. If space and time emerge from something deeper, whether loops, strings, or geometric fragments, then outside the universe might be as nonsensical as asking what's outside a thought. The universe wouldn't expand into a place, it would generate place as it unfolds, like a story writing its own setting. This doesn't just challenge our intuition, it redefines what intuition even means when confronting the raw architecture of reality. So while a complete theory of quantum gravity remains elusive, the search has already transformed our cosmic perspective. Whether through loops, strings, or some yet undiscovered framework, these ideas remind us that the universe's deepest secrets might not lie beyond the horizon, but beneath the very fabric of existence, waiting to be woven into a new understanding of everything. Black holes aren't just cosmic vacuum cleaners, they might be the key to understanding one of the most radical ideas in physics, that our 3-dimensional universe is nothing more than an illusion, a holographic projection of information scribbled on a distant 2-dimensional surface. This isn't science fiction, it's the holographic principle, a theory born from the fiery marriage of quantum mechanics and black hole physics. The story starts with a paradox. When matter falls into a black hole, it vanishes from our universe, but quantum mechanics insists information can never be destroyed. So where does it go? Theorists like Leonard Susskind and Gerard T. Hooft proposed a wild solution. The information isn't lost, it's smeared across the black hole's event horizon, the point of no return, like a cosmic etch-a-sketch preserving every detail of what fell in. This led to an even bolder idea. If a black hole's entire 3-dimensional interior can be encoded on its 2-dimensional surface, could the same be true for our universe? Imagine the cosmos as a giant movie screen with everything we see. Stars, galaxies, even our own bodies, just shadows cast by data flickering on some far-off boundary we can't perceive. In this view, expansion wouldn't mean space stretching into nothingness. It might simply be the unfolding of more complex information on that hidden surface, like a cosmic algorithm generating reality as it runs. The holographic principle turns our intuition inside out. Normally, we think of space as a container, an empty stage where matter moves. But if the universe is a hologram, space itself emerges from something deeper, a network of entangled quantum bits, vibrating in ways we barely understand. It's like realizing the world of a video game isn't made of pixels on your screen, but of ones and zeros hidden in the code. This could explain why the universe appears so finely tuned, with constants like gravity and the speed of light perfectly balanced for life. If reality is fundamentally information, then those constants might just be settings in a cosmic program. But how would this reshape cosmic expansion? If space isn't fundamental, then the universe isn't expanding into anything. It's computing more space. Picture a grid growing not because it's stretching into emptiness, but because new cells are being added to the spreadsheet of reality. Dark energy in this framework might not be a force at all, but a side effect of how information scales as the cosmic hard drive fills up. Even the Big Bang could get a rewrite, not an explosion in space, but the booting up of a cosmic operating system, with space-time itself as the user interface. Not everyone's convinced, of course. Critics argue the holographic principle is more metaphor than mechanics, a dazzling idea without a clear path to experimental proof. But supporters point to tantalizing clues, like the way black holes seem to obey thermodynamic laws. They're entropy proportional to surface area, rather than volume, exactly what you'd expect if information lived on the boundary. Future experiments like gravitational wave detectors sensitive enough to probe Planck-scale physics might one day find echoes of holographic noise in the fabric of spacetime. Whether the holographic principle holds up or not, it forces us to confront a humbling possibility. That space, time, and even the question of what's outside might be illusions, artifacts of a deeper reality we're only beginning to glimpse. If true, the universe isn't just expanding, it's rendering, moment by moment, from a hidden code we've yet to crack, and that changes everything, not just how we think about the cosmos, but what it means to exist within it. Time seems to flow in one direction from past to future, like an arrow shot into the cosmos. But why does the universe follow this same irreversible path, expanding outward rather than collapsing inward? The answer might lie in a concept as familiar as melting ice cubes and as mysterious as the birth of time itself: entropy. Picture a cup of hot coffee left on a table. Over hours, it cools to room temperature, never spontaneously reheating itself. That's entropy in action, the tendency of systems to evolve toward disorder. Now imagine that same principle scaled up to cosmic proportions. The Big Bang wasn't just the beginning of space and matter. It was also the moment when entropy was at its lowest, like a perfectly stacked deck of cards waiting to be shuffled. As the universe expanded, that order unraveled and entropy skyrocketed, driving the arrow of time forward in an unstoppable march toward chaos. But here's where it gets fascinating. The expansion of space itself might be the engine behind time's relentless forward push. Think of the early universe as a compressed spring, packed with energy and potential. When it burst outward, it didn't just create room for galaxies, it created room for change, for events to unfold in a sequence we perceive as time. In this view, time isn't just a backdrop to the cosmos. It's a side effect of the universe's stretching fabric, like a story being written as the pages multiply. Some physicists even speculate that if the universe ever stopped expanding, time might grind to a halt, a frozen moment where entropy maxes out and nothing new can happen. Yet there's a twist. What if the arrow of time isn't just a passenger on the expansion train, but the driver? An alternative theory suggests that time's flow might be more fundamental, with cosmic expansion simply riding the wave. Imagine time as a river carving the path for space to follow. This idea turns the traditional picture on its head, proposing that the universe expands because time demands it, a cosmic domino effect where each moment pushes the next into existence. So which is it? Does expansion create time, or does time enable expansion? The truth might be a dance between the two, a feedback loop where each fuels the other. The early universe's low entropy set the stage for expansion, and that expansion, in turn, allowed entropy to grow, locking time into its one-way trajectory. It's a cosmic chicken and egg puzzle with profound implications. If entropy had been higher at the Big Bang, the universe might have collapsed before stars could form. If expansion hadn't accelerated, time's arrow might have wavered. This delicate balance hints at something deeper. The universe isn't just expanding. It's telling a story, one where time, space, and entropy are intertwined chapters, each shaping the other in ways we're only beginning to decode. And like any good story, the ending is still unwritten. Will entropy win out, leaving the cosmos a cold, static graveyard? Or will the universe find a way to reset the clock, looping back on itself in an eternal cycle? For now, the arrow flies forward, carrying us and the cosmos into the unknown. Dark matter is the universe's silent architect, an invisible hand sculpting the cosmos on scales we're only beginning to map. While dark energy stretches space itself apart, dark matter works in opposition, weaving a vast gravitational tapestry that binds galaxies together in a sprawling cosmic web. Picture the universe as a tug of war between these two titans, one pulling structures apart, the other holding them together, with the fate of everything hanging in the balance. Here's the twist: dark matter doesn't just sit idly in space. Its gravitational pull dictates how galaxies form and cluster, acting like a scaffold for the visible universe. Imagine pouring syrup onto a plate and watching it spread into intricate filaments. That's how dark matter behaves, collapsing into dense knots where galaxies later bloom. Without it, stars would scatter like dust in the wind, never coalescing into the grand spirals and ellipticals we see today. The Milky Way, for instance, is cocooned in a halo of dark matter 10 times more massive than all its visible stars combined. It's the glue keeping our galactic neighborhood intact even as dark energy tries to tear the cosmos apart. Yet dark matter's influence has limits. On smaller scales within galaxies and clusters, its gravity reigns supreme. But zoom out far enough, and dark energy's repulsive force takes over, overpowering dark matter's pull like a rising tide lifting every boat. This cosmic showdown creates a startling paradox. Even as dark matter helps galaxies spin faster and cluster tighter, dark energy ensures those clusters will one day vanish over the horizon, isolated islands in an ever-expanding void. The key to understanding this duality lies in their distribution. Dark matter clumps pooling around galaxies in dense clouds, while dark energy permeates every cubic centimeter of space uniformly. It's like comparing the weight of mountains to the pressure of the atmosphere. One shapes local landscapes, the other influences the entire planet. This difference explains why dark matter dominated the universe's youth, when matter was packed tightly, while dark energy only seized control 5 billion years ago as expansion thinned matter's grip. But dark matter isn't just a relic of the past, it's a time capsule. By studying how its gravitational wells distort light from distant galaxies, a technique called weak gravitational lensing, astronomers can reconstruct the universe's growth over billions of years. These distortions reveal where dark matter hides, mapping the hidden skeleton of reality. Some theories even suggest dark matter might interact with itself in ways we've yet to detect, leaving subtle fingerprints in the motions of stars or the afterglow of cosmic collisions. The deeper mystery: we still don't know what dark matter is. Is it a sea of undiscovered particles, frozen relics from the Big Bang? Or does it hint at gaps in Einstein's gravity, a sign that our equations fail on cosmic scales? Each possibility reshapes how we view the universe's expansion. If dark matter decays or interacts in unexpected ways, it could alter the fate of everything, slowing dark energy's march or accelerating it further. What's certain is this: dark matter and dark energy aren't opposing forces but partners in a cosmic dance, each shaping the universe in its own way. One builds the structures we call home, the other decides how long those structures will last. Together, they write the story of reality, a story we're only beginning to decode. Einstein's theory of general relativity has been the cornerstone of cosmology for over a century, predicting everything from black holes to gravitational waves with uncanny precision. But what if it's not the final word on gravity? Some scientists argue that the mystery of cosmic expansion and the need for dark energy might disappear if we tweak gravity itself. Enter modified Newtonian dynamics, or MUND, a bold alternative that suggests gravity behaves differently on cosmic scales than Einstein predicted. Instead of invoking an invisible force like dark energy, MUND proposes that our understanding of gravity is incomplete, especially in the weak field realms between galaxies. At first glance, MUND's appeal is undeniable. It was originally crafted to explain why stars at the edges of galaxies rotate faster than Newton's laws predict, a discrepancy usually chalked up to dark matter's gravitational pull. But MUND sidesteps the need for unseen matter entirely, suggesting that gravity simply weakens less sharply over vast distances than classical physics assumes. Imagine the difference between a flashlight beam fading predictably in a dark room versus one that mysteriously holds its brightness farther out. If gravity works like that second beam, galaxies' rotation curves suddenly make sense without invoking dark matter's shadowy presence. Some modified gravity theories even extend this idea to cosmic acceleration, proposing that what we call dark energy is just gravity's overlooked quirks on the largest scales. Yet MUND faces its own hurdles. While it neatly explains galaxy rotations, it struggles to account for other observations, like the bullet cluster, a cosmic collision where visible matter and gravitational effects clearly separate, leaving dark matter as the simplest explanation. Worse, MUND adjustments to gravity often require arbitrary mathematical fixes, lacking the elegant universality of Einstein's equations. Critics argue it's like patching a leaky boat with duct tape. It might float a little longer, but it's no substitute for a proper repair. Even its successes come with caveats. For MUND to match galaxy motions, it needs a tiny whisper of dark matter anyway, a concession that leaves many physicists unconvinced. The debate isn't just academic. If MUND or a similar theory were right, it would upend modern cosmology, forcing us to rewrite the rules we use to interpret everything from the Big Bang to black holes. But for now, the evidence leans heavily toward dark energy and dark matter as the dominant players. That doesn't mean modified gravity is a dead-end. Science advances when ideas clash, and MUND persistence reminds us that even the most trusted theories deserve scrutiny. After all, Einstein himself overthrew Newton's gravity, and someday, someone might do the same to Einstein. Until then, the universe keeps its secrets, challenging us to think deeper, question harder, and stay open to the possibility that the truth might be stranger than anything we've dreamed up yet. Light from the farthest galaxies has been racing toward us for billions of years, carrying snapshots of the universe's youth. But here's the unsettling truth: we're living in a rare moment when those ancient beams can still reach us. As cosmic expansion accelerates, countless regions of space are vanishing over the horizon, their light outpaced by the stretching of space itself. Imagine standing on a shore where the tide isn't just rising, it's surging faster and faster, swallowing islands one by one until only the nearest remain. That's the fate of our observable universe. Every second, regions that were once visible slip into darkness, their light now stretched beyond detection, their stories lost to the void. This cosmic horizon isn't a physical barrier. It's a limit stitched into the fabric of reality by the speed of light and the relentless expansion of space. Right now, we can peer about 46 billion light-years in every direction, a bubble containing trillions of galaxies, but over time that bubble will shrink. Distant galaxies won't move away in the traditional sense. Space itself will stretch until their light can no longer bridge the growing gap. Future astronomers, if any exist billions of years from now, will gaze into a night sky stripped of all but the closest galactic neighbors. The cosmic microwave background, that faint echo of the Big Bang, will have redshifted into oblivion. Even evidence of dark energy's existence may vanish, leaving future civilizations with no clue that the universe was ever expanding at all. What makes this even more profound is how it reshapes our understanding of reality. The universe we see isn't just a collection of objects, it's a time capsule, with more distant light offering glimpses further into the past. But as expansion erases those distant signals, we're not just losing space, we're losing time. The early universe's secrets, currently written in the cosmic microwave background and the distribution of ancient galaxies, will become inaccessible. Future scientists might never know about the Big Bang, dark energy, or the universe's true scale. They could conclude, reasonably but incorrectly, that the cosmos is static and small, with no hint of the vast, dynamic expanse we now observe. This raises a haunting question. Are we, too, missing cosmic truths because the evidence has already slipped beyond our horizon? There could have been phases of the universe's history, exotic forms of matter, earlier cycles of expansion whose traces are now lost to us. The accelerating expansion isn't just changing the future, it's erasing the past, leaving us with fragments of a story we'll never fully reconstruct. Yet there's a strange beauty in this cosmic vanishing act. For now, we're privileged witnesses to a universe more visible and vibrant than it will ever be again. We can still trace the threads of cosmic evolution from the first stars to the sprawling web of galaxies. That won't last. The window is closing, and with it, our chance to map the full grandeur of reality. It's a reminder that knowledge isn't just something we discover. It's something we can lose, slipping through our fingers like stardust carried away on an unstoppable tide. Picture two soap bubbles floating in the air, drifting closer until their shimmering surfaces touch and merge. Now imagine that same dance playing out on a cosmic scale, with entire universes as the players. This isn't just poetic metaphor, it's a serious hypothesis in multiverse cosmology, where our universe might be one bubble among countless others, each with its own laws of physics, its own version of reality. According to eternal inflation theory, these bubble universes constantly nucleate in a sea of high-energy false vacuum, inflating rapidly like bubbles in a boiling pot. Most drift apart forever, but occasionally, two bubbles might collide, sending shockwaves rippling through their respective fabrics of space-time. The aftermath of such a collision could be written in the oldest light we can see, the cosmic microwave background. Scientists have scoured this afterglow for peculiar temperature variations or strange circular patterns that might serve as cosmic bruises, evidence of a long-ago impact with another universe. While no definitive signal has been found, subtle anomalies like the infamous cold spot, a mysterious chill in the microwave background spanning nearly 2 billion light-years, have sparked speculation. Could this be the scar of a primordial collision, a dent in our universe's history where another reality brushed against ours? The physics of these collisions would be stranger than fiction. When two bubble universes meet, their differing physical constants and vacuum energies would create a boundary layer, a cosmic frontier where the rules of reality might shift abruptly. Picture standing at the edge of such a collision. One side of you obeys our universe's physics, while the other side might experience stronger gravity, faster light, or even extra dimensions. The energy released could spark secondary Big Bangs, birthing new universes within the wreckage of the old. Yet the challenges of proving any of this are staggering. Bubble collisions would likely be rare, and their imprints faint after billions of years of cosmic expansion. Even if we found a candidate signal, distinguishing it from random fluctuations or other astrophysical phenomena would require unprecedented precision. Future telescopes, like the Simons Observatory or next-generation space-based detectors, aim to map the microwave background with finer detail than ever, hunting for these elusive fingerprints. What's fascinating is how these ideas force us to rethink the very nature of reality. If bubble universes exist, then the cosmos isn't just vast, it's layered, with dimensions and physics beyond our perception. The question isn't just whether we're alone in the universe, but whether we're alone in the multiverse. And while the evidence remains speculative, the mere possibility reshapes our cosmic perspective, turning the universe from a solitary stage into one act of an endless play, with collisions, births, and endings we've only begun to imagine. The question of what lies beyond the expanding universe isn't just a scientific puzzle, it's a philosophical labyrinth that's tangled thinkers for centuries. Long before telescopes peered into deep space, philosophers like Gottfried Leibniz wrestled with the idea of a self-contained cosmos. He argued for a principle of sufficient reason, insisting that everything, including the universe, must have an explanation within itself. To Leibniz, asking what's outside the universe was as nonsensical as asking why existence exists at all. The universe, in his view, wasn't a thing in a place. It was the totality of all places, needing no external container. This idea echoes startlingly in modern cosmology, where space-time isn't expanding into anything but generating its own context as it grows. Immanuel Kant took a different approach, probing the limits of human intuition. He distinguished between the noumenal world reality as it truly is and the phenomenal world, the reality we perceive. For Kant, questions about the universe's boundaries were classic examples of how our minds, wired for finite experiences, stumble when confronting the infinite. We instinctively picture the cosmos as a balloon growing in a room because that's how objects in our daily lives behave. But what if the universe defies such analogies? Kant's insight suggests the very concept of an outside might be a cognitive mirage, a projection of our terrestrial logic onto a reality that operates by entirely different rules. Today's physicists unknowingly channel these philosophical debates when they describe cosmic expansion. The inflationary multiverse theory, for instance, posits that our universe is one bubble in a frothing sea of others, a modern twist on Leibniz's self-sufficient cosmos, but with extra dimensions. Meanwhile, quantum gravity theories like loop quantum cosmology imply the universe might be self-contained in a more literal sense, with space-time woven from discrete, self-referential loops. These scientific models don't just answer old questions, they reframe them, showing how what's outside might be as meaningless as asking what's outside a circle. Yet the tension between containment and infinity persists. Some philosophers of science argue that physics, in its quest to avoid metaphysics, often smuggles in unexamined assumptions. When cosmologists say the universe doesn't need an outside, are they describing nature or imposing a mathematical convenience? The holographic principle, for example, suggests reality might be a projection from a distant boundary, a tantalizing blend of Leibniz's self-containment and Kant's duality. Here, the outside isn't a place but a deeper layer of information, a cosmic code generating the illusion of space. This interplay between science and philosophy reveals something profound. our struggle to picture cosmic expansion isn't just about missing data, it's about the limits of language and imagination. The universe doesn't owe us an answer that fits human-scale metaphors. Whether it's Leibniz's rational totality, Kant's epistemological boundaries, or a physicist's quantum foam, each perspective illuminates facets of the same enigma. The real frontier might not lie beyond the cosmic horizon, but in understanding how to think beyond the horizon of our own minds. What if the universe isn't just expanding? What if it's rendering? The simulation hypothesis, once relegated to science fiction, has clawed its way into serious scientific debate, proposing that our entire cosmos might be an artificial construct, an ultra-advanced computer simulation running in some higher reality. If true, cosmic expansion wouldn't be a physical process at all, just a line of code, a programmed parameter designed to create the illusion of an infinite, evolving universe. This isn't just a wild thought experiment, it's a lens that forces us to question the very nature of reality. Think of it like a video game. In a sprawling open-world game, the landscape doesn't exist all at once. It loads dynamically as the player moves, generating new terrain while discarding what's no longer needed. Could the universe work the same way? Expansion might simply be the system allocating more memory, filling in pixels of space-time as needed to maintain the illusion of continuity. The speed of light, in this view, could be the processing speed limit of the cosmic computer, and quantum indeterminacy might reflect the resolution at which reality is rendered. Even dark energy could be a placeholder, a mathematical patch to keep the simulation running smoothly as it scales up. But how plausible is this? The argument gained traction when philosopher Nick Bostrom pointed out that if advanced civilizations routinely run ancestor simulations recreating their past in digital form, the statistical likelihood we're in the real universe shrinks nearly to zero. After all, there'd be billions of simulated minds for every biological one. Physicists have even proposed ways to test the idea. Some suggest looking for computational shortcuts, glitches in the simulation, like subtle inconsistencies in high-energy particle behavior or unexpected limits in the precision of physical constants. Others hunt for evidence of pixelation in spacetime itself, anomalies that might reveal the underlying code of the cosmos. Yet the simulation hypothesis isn't without critics. Many scientists argue it's unfalsifiable, a clever metaphor masquerading as science, with no clear way to prove or disprove it. Worse, it risks being a metaphysical dead end. If every unexplained phenomenon can be hand-waved as part of the simulation, it could stifle genuine scientific inquiry. And then there's the infinite regress. If our universe is a simulation, what about the reality running it? Is that a simulation too, turtles all the way up? What makes the idea compelling isn't its literal truth, but how it reframes our assumptions. If the universe can be simulated, then physical laws aren't necessarily fundamental. They're algorithms, adjustable settings in a cosmic engine. Expansion isn't an inevitable feature of space-time, it's a design choice. This flips traditional cosmology on its head, turning existential questions into technical ones. Not, why is the universe expanding, but why did the programmers make it expand? Whether the simulation hypothesis holds water or not, it underscores a deeper truth: our models of reality are always provisional, shaped by the tools and metaphors of our time. Centuries ago, the universe was a mechanical clockwork. Today, it's a quantum computer. Tomorrow's metaphors may be stranger still. The real lesson isn't that we're living in a simulation, but that reality, whatever its nature, is far more malleable and far more mysterious than we've dared to imagine. Human intuition evolved to navigate a world of trees, rivers, and predators, not to comprehend the infinite stretch of cosmic expansion. There's something profoundly humbling about realizing that some questions might forever dance just beyond the reach of our understanding, not because we lack curiosity, but because the universe operates on scales and in ways that defy the very frameworks of our thought. Consider the humble goldfish in its bowl. Its entire reality is shaped by the curvature of glass, distorting the world beyond into meaningless blurs. Are we any different, peering out at a cosmos filtered through the limitations of our biology and physics? This isn't surrender, it's clarity. Science thrives on solvable puzzles, but part of its power lies in recognizing the boundaries of its own lens. Take the cosmic horizon. No matter how advanced our telescopes become, we'll never see beyond it because the space between us and those distant regions expands faster than light can traverse. It's not a matter of better technology, it's baked into the fabric of reality itself, like a character in a novel unable to read the bookshelf their story sits upon. Some truths might be perpetually veiled, not by our tools but by the universe's own rules. Yet here's the paradox that fuels discovery. The unknowable isn't a wall, it's a compass. Every time we've bumped against the edges of understanding, from quantum weirdness to black hole singularities, it hasn't stopped science, it's redirected it. When 19th century physicists thought they'd nearly solved everything, the discovery of radioactivity shattered their confidence and unlocked the atomic age. Today's unanswered questions what space expands into, whether multiple universes exist, aren't roadblocks. They're invitations to refine our theories, invent new mathematics, and imagine possibilities we've yet to dream. Philosopher Ludwig Wittgenstein once argued that the limits of my language mean the limits of my world. Our struggle to articulate what's beyond expansion reveals how language itself strains under cosmic weight. We say outside, but that implies a container. We say nothingness, but quantum physics shows us even vacuums boil with potential. Perhaps the answer isn't finding better words, but transcending the need for them, developing new modes of thought that don't rely on familiar metaphors of balloons or bubbles. The beauty lies in the tension between knowing and wondering. Dark energy accelerates the universe's expansion, but it also accelerates our hunger to understand. Each generation inherits deeper mysteries than the last, not because we're failing, but because every answer peels back another layer of the cosmic onion. Whether we ever grasp what lies beyond the expanding universe may matter less than the fact that we keep asking, that we're a species unwilling to accept that any horizon, no matter how distant, should go unchallenged. After all, the universe didn't promise us answers, it only promised us wonder. The next generation of telescopes isn't just upgrading our view of the cosmos, it's rewriting the rules of the game. Take the James Webb Space Telescope, already revolutionizing astronomy with its infrared eyes. While Hubble showed us galaxies from the universe's teenage years, Webb peers into its infancy, capturing light from the first stars that flickered to life over 13 billion years ago. But here's why that matters for cosmic expansion. By studying these ancient stellar nurseries, Webb can measure the early universe's growth rate with unprecedented precision, testing whether dark energy's strength has changed over time. Imagine comparing a toddler's height scrawled on a doorframe to an adult's. Webb lets us see the full growth chart of the cosmos, revealing whether expansion has always accelerated or if dark energy is a recent cosmic development. Then there's the Vera Rubin Observatory, set to begin its legacy survey of space and time in 2025. This ground-based behemoth won't just take pretty pictures. It'll create a decade-long time-lapse of the universe, tracking billions of galaxies as they're carried apart by expansion. Its secret weapon, weak gravitational lensing, the subtle warping of light as it passes through dark matter's invisible webs. By mapping these distortions across the sky, Rubin could settle the Hubble tension once and for all, revealing whether the discrepancy in expansion rate stems from measurement errors, unknown physics, or something even stranger, like a local void where our Milky Way sits in an underdense bubble, skewing nearby observations. But the real wild cards are missions like LISA, the Laser Interferometer Space Antenna. Scheduled for the 2030s, this trio of spacecraft will float millions of miles apart, connected by lasers to detect gravitational waves at frequencies impossible to catch on Earth. Why does that matter for expansion? These ripples in spacetime could carry echoes from the universe's first trillionth of a second, potentially revealing whether inflation really happened, and if so, whether it left behind a multiverse of bubble universes. Picture listening to the cosmic equivalent of a vinyl record. The pops and crackles of primordial gravitational waves might betray collisions with other universes, like needle skips revealing hidden tracks. Meanwhile, projects like the Simons Observatory and CMB-S4 are doubling down on the cosmic microwave background, hunting for swirling patterns called B-modes that could signal inflation's quantum origins. If detected, these imprints would confirm that space once expanded faster than light itself, and possibly uncover whether our universe is one of many in a vast inflationary landscape. It's like finding fingerprints on a window pane. The patterns might tell us not just who was there, but how many others were in the room. The coming decade won't just fill gaps in our knowledge, it could tear open entirely new chapters. What if Webb spots galaxies too mature for their age, hinting at cycles of expansion before the Big Bang? What if Rubin finds expansion rates vary in strange directions, suggesting our universe is asymmetrical? Every new instrument is a flashlight in a cosmic attic, illuminating corners we didn't know existed. And with each discovery, the mystery deepens, proving once again that the universe's greatest trick isn't hiding its secrets, it's showing us how much we've yet to even question. One of the most persistent myths about cosmic expansion is the idea that the universe is spreading outward like debris from a gigantic explosion. It's an easy mistake to make. After all, we're used to seeing objects move through space, so it's natural to assume galaxies are hurtling away from some central point into pre-existing emptiness. But here's the twist: space itself wasn't flung outward from a single location. Instead, it's stretching everywhere at once, like a loaf of raisin bread rising in the oven where every raisin moves away from every other raisin, not because they're traveling through the dough, but because the dough itself is expanding. This distinction between movement through space and the stretching of space is crucial, and it's where everyday intuition fails us. When we watch fireworks, we see sparks shooting outward into the night sky, leaving a central point behind. The universe doesn't work that way. There's no center of expansion to point to, no cosmic ground zero where the Big Bang happened. Instead, imagine every point in space as equally special, with all regions growing apart simultaneously. A galaxy 10 billion light-years away isn't just moving away from us, it's seeing its own neighbors recede too, each observer in their own pocket of reality, witnessing the same uniform stretching of spacetime. Another common misconception is that galaxies are zooming through space at incredible speeds. While it's true that distant galaxies appear to recede faster than light, they're not breaking any cosmic speed limits. The expansion of space itself doesn't have the same constraints as objects moving within space. It's like dots drawn on a rubber band. As you stretch it, the dots separate, but they aren't sliding across the material. The space between them is literally growing, and the farther apart they are, the faster they seem to move away. That's why we can observe galaxies whose light has been stretched so much by cosmic expansion that their wavelengths are now far beyond the visible spectrum. They're not moving in the traditional sense. The road beneath them is elongating. Then there's the myth that expansion means everything is getting bigger: planets, stars, even atoms. But gravity and other fundamental forces tightly bind local structures, overriding the gentle tug of cosmic expansion. Our Milky Way isn't inflating, and neither is your coffee cup. Only on the largest scales, where gravity's grip is weakest, does expansion dominate. It's the difference between a rubber band stretching and a steel cable holding firm. One yields easily while the other resists. Perhaps the most poetic misunderstanding is the idea of the universe expanding into something. We instinctively picture a growing bubble surrounded by, well, what? Empty space, another universe. But if the universe is all there is, then outside might not even be a meaningful concept. The expansion isn't filling a void. It's generating space as it goes, like a never-ending roll of fabric unfurling from within. Trying to visualize what's beyond might be as futile as a flatlander trying to imagine the third dimension. The truth could be far stranger. Space isn't expanding into anything because into implies a container that doesn't exist. Clearing up these myths isn't just about setting the record straight. It reshapes how we perceive reality. When we stop imagining galaxies racing through darkness and instead picture space itself stretching, carrying them along like leaves on a widening river, the universe becomes less like a machine and more like a living thing, breathing itself larger with every passing moment. And that shift in perspective, that's where the real awe begins. Long before telescopes and equations, humanity gazed at the stars and wove stories about what lay beyond the shimmering curtain of night. The ancient Norse imagined Yggdrasil, a cosmic tree whose roots and branches held the 9 realms together, not as a metaphor but as literal geography. Hindu cosmology described an infinite egg of Brahmanda, where our universe floats among countless others like bubbles in a celestial ocean. These weren't just fanciful tales, they were early attempts to reconcile the same question that haunts modern cosmology. If the universe has edges, what exists on the other side? Science fiction has taken up this torch with dazzling creativity. In Arthur C. Clarke's The City and the Stars, the universe is a sealed simulation, its inhabitants unaware they're trapped within an artificial horizon. The film Interstellar visualized the cosmic frontier as a tesseract, a higher dimensional labyrinth where time becomes a physical dimension. Even children's media like The Magic School Bus played with these ideas, sending a mess. Frizzle's class hurtling past galaxies only to confront a literal edge of space painted like a theater backdrop. What unites these visions is the instinct to personify the unknown, to give the void a face we can recognize. Artists, too, have wrestled with the ineffable. The haunting paintings of Remedios Varo depict cosmic expansion as intricate clockwork, with celestial gears turning in harmony. Musician Björk's album Biophilia translates astronomical phenomena into sound, her track Cosmogony layering choral harmonies to evoke the Big Bang's reverberations. These works don't just illustrate science, they interrogate it, asking how it feels to inhabit an expanding universe. Is it exhilarating or isolating? Like floating or falling, the parallels between ancient myths and modern theories are startling. The Aboriginal concept of the dreamtime, a timeless dimension underlying reality, echoes the quantum foam of spacetime at Planck scales. The Buddhist idea of Indra's net, where jewels reflect each other infinitely, mirrors the holographic principle's suggestion that our 3D universe might be projected from a 2D boundary. Whether through sacred texts or speculative art, humanity keeps returning to the same themes: containment, connection, and the vertigo of infinities. This cultural tapestry reveals something profound. The mystery of cosmic expansion isn't just a scientific problem, it's a mirror. How we imagine the universe's edges reflects how we see ourselves. Are we passengers on a solitary ship or threads in a vaster weave? The answers shift with the times, but the question endures, as timeless as the stars themselves. And perhaps that's the greatest lesson, that in chasing the horizon, we're also charting the contours of the human spirit. Mathematics is the silent architect of cosmology, translating the universe's grand design into equations that fit on a napkin. At the heart of this cosmic blueprint are the Friedmann equations, deceptively simple formulas that describe how space stretches over time. Named after Alexander Friedmann, who derived them in the early 1920s, these equations emerged from Einstein's general relativity, yet they revealed something Einstein himself initially resisted: a dynamic, evolving universe. They tell us that if you know the density of matter and energy in the cosmos, you can predict its fate, whether it will expand forever, collapse, or teeter on a knife's edge. But here's the catch: while these equations model expansion flawlessly, they say nothing about what space is expanding into. Math can describe the balloon's surface, but not the room it might be filling. This raises a deeper question. Is mathematics merely a tool for modeling, or does it reveal something intrinsic about reality? Think of it like musical notation. A symphony's sheet music captures every crescendo and pause, but it can't convey the warmth of the violin's wood or the hush of an audience holding its breath. Similarly, the Friedmann equations quantify expansion rates and critical densities, yet they remain silent on the visceral experience of an infinite cosmos. They're a map, not the territory, a powerful abstraction that sometimes feels eerily detached from the tangible universe it describes. Yet math's predictive power is undeniable. Long before telescopes spotted distant supernova racing away from us, Friedmann's work hinted at cosmic expansion. Decades before dark energy's discovery, his equations had placeholder terms for energies we hadn't yet imagined. This uncanny accuracy suggests math isn't just a human invention, it's woven into the fabric of reality, a language the universe speaks fluently. When we solve for the curvature of space-time or the acceleration of galaxies, we're not inventing rules, we're deciphering them, like archaeologists brushing dust off ancient runes. But can math answer the existential questions? When we ask what lies beyond the expanding universe, equations hit a wall. The Friedmann models describe a self-contained system, a cosmos with no need for an outside. To demand more is like asking a GPS to navigate beyond the edge of its map. The software wasn't built for that. Some theorists argue this limitation reflects a deeper truth. The question itself might be malformed, like asking for the square root of a sonnet. This tension between math's precision and its blind spots fuels fierce debates. Max Tegmark's mathematical universe hypothesis takes things further, proposing that reality isn't just described by math, it is math. In this view, the universe isn't a physical thing expanding into void. It's a mathematical structure, with expansion just another equation in an infinite textbook. Critics counter that this reduces existence to a cold, bloodless formalism, stripping away the texture of lived experience. Can a quark's spin or a supernova's glow truly be just numbers in a cosmic spreadsheet? Perhaps the most humbling lesson is how often math outruns intuition. Quantum mechanics shattered classical notions of locality. Relativity twisted time into a pretzel. Now, as we confront cosmic expansion, we're forced to accept that the universe's true nature might not just defy common sense, it could defy all possible visualization. The mathematics whispers of higher dimensions, multiverses, and holographic boundaries, realms where words and images fail. So where does this leave us? Math is the compass guiding us through the cosmic wilderness, but it can't tell us why the wilderness exists or what lies beyond the last coordinate. The Friedman equations are a masterpiece of human ingenuity, yet they're also a reminder. Some mysteries dissolve under the glare of calculation, while others deepen, leaving us to wonder if the universe's ultimate truths are written in a language we've only begun to stumble through. Imagine waking up to headlines announcing that scientists have finally cracked the cosmic code, that we now know what lies beyond the expanding universe. The revelation wouldn't just rewrite textbooks, it would dismantle and rebuild humanity's collective worldview. For centuries, our place in the cosmos has been framed by mystery, with religions offering creation stories and science offering theories, but never absolute answers. A discovery of this magnitude would force a reckoning between faith and empiricism, unlike anything since Galileo pointed his telescope at Jupiter. Some might see it as the ultimate triumph of human curiosity, while others could interpret it as a threat to the sacred unknown that's long defined spiritual traditions. The very concept of a divine creator could shift if we uncover evidence of a multiverse or higher dimensions. Would gods reside in those realms, or would the universe become its own self-contained deity? Beyond theology, such knowledge would ripple through every layer of society. Consider how the space race of the 20th century galvanized global cooperation and competition, sparking advancements in computing, materials science, and telecommunications. Learning the true nature of cosmic expansion could ignite a similar technological renaissance. If we discovered our universe floats in a higher dimensional bulk, as string theory suggests, engineers might dream of tapping into those dimensions for energy or transportation. Concepts like warp drives or wormholes, once confined to sci-fi, could become serious research agendas, not because we'd have the immediate ability to build them, but because understanding the universe's architecture might reveal new physical laws to exploit. Yet with such power comes peril. History shows that paradigm-shifting discoveries often exacerbate inequalities before uplifting humanity. The atomic bomb emerged from unlocking the secrets of the atom. What destructive potential might lie in manipulating the fabric of space-time itself? Nations or corporations controlling access to cosmic-scale physics could wield unimaginable leverage, creating a new arms race not for weapons, but for dominion over the fundamental forces of reality. Ethical frameworks would need to evolve at light speed to prevent a world where the keys to the universe belong only to the privileged few. On a more intimate level, this knowledge would challenge our sense of meaning. Existential dread already lurks in the shadow of cosmic insignificance. What happens when we learn our universe is just one bubble in an infinite foam? Would we double down on human exceptionalism, or embrace a humbler role in a reality vaster than we dared to imagine? Art, literature, and philosophy would explode with new movements, from nihilistic despair to transcendent awe. The Renaissance reshaped culture after proving Earth wasn't the center of the solar system. This would be 1,000 times more profound. Perhaps the most beautiful outcome would be the unification it could inspire. Faced with proof of our cosmic context, petty divisions might pale against the shared wonder of existence. Or we might fracture into factions debating how to interpret or exploit the revelation. One thing's certain, the quest to understand our place in the universe isn't just about mapping galaxies or solving equations. It's about discovering who we are when confronted with the infinite. And that journey, no matter where it leads, is what makes us truly human. As we stand at the edge of cosmic understanding, peering into the void beyond our expanding universe, it's not the answers that define us, but the questions. The journey to unravel this mystery has taken us from the quantum foam of spacetime to the holographic edges of reality, from the echoes of the Big Bang to the invisible grip of dark energy. And yet, the more we learn, the more the universe twists into new shapes of wonder. Perhaps that's the true nature of exploration, not to arrive at some final destination, but to keep moving the horizon farther out, ensuring we'll always have room to grow. Think of all the brilliant minds who have grappled with this puzzle: Einstein dismissing his own cosmological constant, Hubble staring through his telescope as galaxies fled into the red, modern physicists wrestling with higher dimensions and multiverses. Each generation builds on the last, not just adding pieces to the cosmic jigsaw, but sometimes realizing the puzzle itself is far bigger than anyone imagined. What seemed like an edge might just be a fold. What looked like emptiness could be a canvas we're not equipped to see. This is why the question matters more than the answer. It drives us to build telescopes that peer back in time, particle colliders that recreate the universe's first moments, and equations that bend the mind to their will. Every child who looks up at the stars and wonders what's out there is part of this grand tradition. You don't need a PhD to feel the awe, just the willingness to sit with the unknown and let it stretch your imagination. So while we may never know for certain what lies beyond the cosmic horizon, we've discovered something equally profound: a universe that refuses to be small, predictable, or easily tamed. Whether it's a multiverse bustling with alternate realities or a self-contained cosmos generating space from within, one truth remains: we're part of something vast, strange, and humblingly beautiful. The night sky isn't just a sight to behold. It's an invitation to keep questioning, keep exploring, and never stop marveling at the fact that we get to witness this cosmic story at all. Who knows what revelations the next century will bring? Maybe you'll be the one to spot the flaw in our theories, or dream up the equation that cracks the code. Until then, let the mystery linger like the afterglow of the Big Bang itself, a reminder that the universe's greatest gift isn't the answers it gives, but the questions it inspires. So take a moment tonight to look up. That endless expanse isn't just expanding.